Hi, this is the fourth video in the enthalpy changes section, and in this one I'm looking at Hess's law. Now, Hess's law is often quite difficult to get your head round. We're going to think of, first of all, with Hess's law, that reactions can take more than one route. So if we had our reactants going to our products, it might go very simply, just straight from reactants to products, or we could go to an intermediate first and then to the product, so a bit more long-winded. So there are different routes we can take. Regardless of route, the enthalpy change, so change in enthalpy, will be the same for both routes taken. So if you go the really long-winded way, the change in enthalpy will be the same regardless of how you got there. And we take advantage of that because a problem that often occurs in working out these enthalpy changes is we can't do them experimentally. And if we can't do them experimentally, for whatever reason, then we can take advantage of Hess's law in order to then find out what the enthalpy change would be. I'm going to start with this reaction. It's this slightly unusual reaction, the incomplete combustion of carbon. So in this we've got carbon, we're reacting with oxygen, and in this case it's going to form carbon monoxide. Really, really difficult to do because we'll probably get carbon dioxide forming as well. It's very difficult to limit perfectly the amount of oxygen so only carbon monoxide forms. So to get the enthalpy change, which I'm going to call enthalpy change 1, and this is the enthalpy change of reaction, could have put delta RH in there, is really, really tricky experimentally. But what I can do experimentally is to add an excess of oxygen to carbon to form CO2. And I get an enthalpy change value for this equal to minus 394 kilojoules per mole. So that I can do quite easily in the lab. As long as you've got an excess of oxygen, that goes forward quite nicely. I can also take carbon monoxide and add an excess of oxygen to that to form the same thing, CO2. And that gives me an enthalpy change as well. So if you really want to challenge here, stop the video here and see if you can work out how you can put these values together to work out that enthalpy value there. So if we look here, if we take carbon plus, we've already got half an oxygen there, so we only need another half an oxygen molecule. So essentially we're adding half an oxygen molecule onto here, we get CO2. And this I'm going to call enthalpy 2, or enthalpy change 2. And if we take carbon monoxide and add half O2, or combust it, we get CO2 as well. And that I'm going to call enthalpy 3. So we've got two routes here that start with the same reactants. The products in this case are CO2. The first route is to go via carbon monoxide first, and then to carbon dioxide. The second route, more direct, is just to go straight to carbon dioxide. And what I've done to identify these two routes is looked at the direction of the arrows. Now these two arrows are going clockwise, so going in the same direction, this one anti-clockwise. And in this case, delta H1 plus delta H3 equals delta H2. And I have those values. Well, I have two of those values. I've got delta H2 is minus 394. And delta H3 is minus 284. I won't put the units in for this, just to save space. So delta H1, our initial one we're trying to work out, plus minus 284 is going to equal minus 394. So if I take minus 284 from both sides, I will get minus 110 kilojoules per mole. And that's how I can use this data to work out what delta H1 was. So that's using combustion data, which we can often work out very, very easily and do in the labs. It's often quite easy to work out those values. Second example I'm going to look at, slightly different. But we're going to use a very similar method. So in this one, I'm taking an acyl chloride, reacting with ethanol, that forms an ester, and HCl. Now in this case, what I'm going to do is I can work out experimentally how much the enthalpy change of formation for each one of these. And the elements on this side and atoms are equal to the elements and atoms on this side. So we've got two enthalpy formation, both coming from the same number of atoms. So we've got 3 carbons. So carbon, under standard conditions, is a solid. I've got 3 of them. Plus, I've got 3, 8, 9 hydrogens on this side, 3, 8, 9 hydrogens on that side. So that's 4.5 H2 gas. Then oxygens, 1, 2 oxygens, so oxygen's a diatomic molecule, plus, so we've got Cl, so half a Cl molecule. This time the direction the arrow is going to go different because I'm going to react these to form this, and I can react these to form this, and I know how much energy is given off when I form these two, because it's CH3COl, which is minus 272.9 plus minus 277.1, and this way, because it's minus 479.3 plus minus 92.3. So I know those amounts of energy, and I can use that to work out the enthalpy change here. So again, looking at the arrows, I can see, starting from here, I can go this way, or I can go this way to those products. And if I add this and this, that's going to equal this over here. So if I go 272.9 plus 277.1, I've got here minus 500 plus the enthalpy we're trying to work out is going to equal minus 479 plus it's going to equal 571.6 kilojoules per mole, minus 571.6 kilojoules per mole. So that's quite a nice one to do with 500 there. We know then that the enthalpy change in this reaction is going to be minus 71.6 kilojoules per mole. So this has just taken advantage. It's looked at the arrows and gone, well, these two both go from this starting point to there. This one just goes straight there. So Hess's law, regardless of the route, energy is going to be the same. So this is going to have the same energy as this. And then just a bit of basic maths to do there.